Okay, so let's get started. So the first like two sections are kind of going to be review on like not review, but they'll like have a lot of connections with like our take home challenge and kind of like this like they'll be like about things that would have been helpful in doing that. So like so image basics, right? And for all these slides, I like put the links to like the things that I use on like the top right if it's relevant. But yeah, so like when we think about uh images and stuff, pretty simple. Like you got pixels at every like XY coordinate. They're like the main standard is like RGB. But there's also like HSV, which represents the same color space or almost the same color space in hue, saturation, and value. It's like slightly different. But for our purposes, they're pretty much identical. And sometimes it's useful like for analysis to convert between the two like standards. Um, but yeah, I'm sure you guys like had experiences in the challenge and stuff. And then like when we're like a lot of our algorithms are like single channels and multi-channel. So for those purposes, you might want to convert like these three like units channels of information into just one. So like that could involve RGB to grayscale or HSV to just the value. But like always keep that in mind and when you gotta like convert things back and forth between different sort of units. Um yeah. And so like let's go to our first sort of topic that maybe most of you haven't seen yet, convolutions. Um it might just like make the most sense for me to jump into the notebook at this point. But basically, it's trippy. Um, okay. So, and this is also in the mono repo. So, like, if you guys want to run this like side by side with me, you can. It's in like the course folder. You just pull from it. But basically, here. So I just have like some like regular like image that I've like found on the internet. We're just gonna apply a series of convolutions to it. But um, mm, So like a way to think about convolutions is that you have kernels. Like these are three different kernels. And what a convolution does is that you go element when you apply a convolution onto an image, you go element by element on the image, and then you kind of take a weighted sum based on a convolution. So like, oh, there's no space. You guys can like see this area, right? I hope. Okay, so like let's say you got like, I don't know, you have an image and like let's just assume it's single channel for now. If you wanted to apply just like RGB, you would apply the convolution on each of the RGB values, or you'd like take the grayscale as I mentioned before and like apply the convolution to that like single channel value. But let's say you have the single channel like image, like 1, 3, 7, 2, 0, -1, 3, I don't know, 4, 5. Applying like a kernel of like any arbitrary size really, like let's just say it's like A, B, C, D, E, F, G, H, I. This would this operation would equal I guess in this context, since the kernel is so big, it would just equal zero it would equal 8 times 1 plus or it's the best way to like show this. You like you take the you wait, hold on. Let me add more numbers to this. So just imagine taking this like matrix and sliding it over like this image, right? So like the top list, most place you can like put this kernel in is it is like for this top 3 by 3 square, right? Like anywhere past this, like you would have I guess stuff on edge, and that doesn't really apply. So like you start from here, and then basically this kernel would basically collapse all the values in this 3 by 3 square onto this single element, right? And so and it's like when you apply this like 3 by 3 square onto the single element, you get one value. And then next you like slide it over and apply it for like this square. And then you get another value. So like after taking this 3 by 3 square and putting it onto this 4 by 4 image, you get basically 4 values. So this would output like a 2 by 2 matrix essentially. You get a 2 by 2 matrix, I guess called C1, C2, C3, and C4, where I guess into the details of the computation, C1 is equal to A times 1 plus B times 3 plus C times 7 plus D times 2 plus E times 0 plus F times -1, etc. And just basically the weighted sum of all of these values and into one value, and that becomes C1. And then you slide the kernel over to the right, and you apply the same exact like sort of weighted sum to the values that are the neighbors of this matrix. And so with kernels, you're essentially like taking this like you're basically like sort of applying this identical aggregation function to all the pixels in the neighborhood of a single value, and then you're like making it, and you're making that value like the representative value like of the operation. So like and the reason this is useful for us is because you can like design like interesting like kernels, right? So like this blur kernel, for example, right? You're basically taking for each pixel, you're basically just taking the values of its top, bottom, left, and right values, and like basically taking the average of it, right? And so what this would do is that it would just make each pixel the average of its surrounding like values, which in effect would kind of blur the image, right? With this left soluble like kernel, it's slightly different. Can somebody guess like maybe like what the effect of this kernel is? Just thinking about it heuristically. It's like what would the value of this kernel look like when you're at a pixel uh that's like kind of in the background. So like in other words, all the values around it are like same like equal to it. What would the value of this kernel be? It would be 0, right? So like basically this kernel for any pixels that are in the background or in any region of like uniformity will output 0. Now let's say you're on like a pixel where the values on the left are different from the values on the right, like maybe some sort of edge, right? What would the value of this um like kernel operation be? It would be non-zero, right? So like if you can like kind of guess and reason, like this kernel basically almost identifies edges that are vertical, right? Because like for any region that's uniform, it gives you 0. And like more specifically, when you hit a region that has higher value on the right and lower value on the left, you get like a really negative value. And when you get to a region that's like lower value on the right and higher value on the left, you get like a really positive value. And in a sense, you get like the vertical like edges in an image. And so like let's just run this. And like like this is obviously identity. Like for every like region, we're just like taking the middle element. And like kernels can be of different sizes. I've just shown 3 by 3 for convenience, but like you can imagine like as you choose kernels of bigger and bigger sizes, like the blur operation would become more averaging almost, and it would incorporate information from like farther and farther regions from it from your original input image and vice versa. Um, Now sharpen. Okay, cool. And then the nice thing about kernels is that they like you can like do math with them. So like I've defined the sharpen kernel as basically your original identity kernel plus the difference between your identity and blur times like some sort of arbitrary intensity that you've chosen that I've chosen. I think I set it to like 5 or something. But the reason this works is because like the difference between your intensity and blur kernels like is kind of like a measure of like sharpness, right? Like um whatever like whatever you need to add to your blurred version of your image to get your original image is like what you would need to sharpen it in a sense. And it's like this turns out to be like a pretty good heuristic for a sharpening kernel. And I'm just gonna run like this code to like show you guys what it looks like, right? So this is like our original like grayscale image that I used to like bring it down to a single channel. This is the left solo filter. So like as you can see, like kind of all the vertical edges are like kind of teased out. Um, the blur filter kind of makes it kind of blurry, and the sharpening filter has the opposite effect. Um, and the reason like convolutions are important because they apply the same operation on all pixels in your image like equally. In other words, it treats every single pixel equally. So it's useful for like, you know, I guess decreasing the dimensionality of your input in a way that might be useful for your task. And that's why it's important to us. Um, okay, on to the next slide. So these are what kernels are, like just a quick recap. It's a weighted sum of like whatever pixel elements you might have, and your filters can like highlight like patterns, as I said, like edges, textures for sharpening, etc. And yeah. Uh Cool. And then like onto like other like basic image processing things that you might use in your challenge. You might use a smoothing filter or convolution, like a Gaussian blur, where essentially you basically have the same sort of filter as like what you see here, but like it's like weighted like as a 2D Gaussian distribution, right? Or you might have a sharpening filter, as I just mentioned. You can also like scale and transform, rotate your images. Um, so I guess here's an example, and these are all operations you can do in like CV2. Like by resizing would like make it smaller. You can rotate it, you can flip it, you can crop it. These are all pretty straightforward, I think. And like with all these tools, I guess you can kind of start like doing things like candy edge detection. And so like to get into that, I think basically all of you guys use it in your like take home challenge, but like to like look at the implementation, there's kind of 5 like broad steps, right? You have like an initial noise reduction stage where you smooth the image to reduce noise. Can somebody tell me why this is like important in like in something like counting edge detection, like why you would want to like, I don't know, like reduce the noise in the image, like take information away in a sense. Any guesses? You're trying to detect edges, right? So why would smoothing be helpful? Yeah. Yeah. So like this is actually an idea that comes up later in key point detection. But like basically important things in your image, like edges and stuff like that, should still be there after you blur the image, right? Because they're the defining characteristics of your image. It's actually noise that you kind of filter out when you start to blur the image. So like it's actually something we want, right? We are in theory like throwing away information, but it's information that we don't care about in a sense. Um, cool. And the second step, oh, I forgot to mention this. So like remember the funny looking like Sobol like edge detection thing that I mentioned like earlier, like for like left edge detection. It turns out that like there's math that goes behind. Like basically you can choose any arbitrary direction and you can like create a filter that like teases out edges in that direction. So like in this case, this teased out edges in like the vertical direction, but you can like kind of specify any arbitrary like gradient direction and like do it for you. You can imagine like rotating this kernel like whichever way you want. But this turns out really important for candy edge detection because what you do is that basically you first smooth the image and um you get like the changes in the vertical and horizontal directions for every pixel, right? And then in that sense, you're able to like find pixel values where either it has a lot of change vertically speaking, a lot of change horizontally speaking, or a lot of change in like a certain direction, right? And then so basically now you have a bunch of candid edge strength values, right? And then you run it through an algorithm called non-maximum suppression where it it takes each pixel and it's like corresponding like I don't know edge strength value and it like removes pixels for which it's like not the biggest out of anything in this region. And then it goes through a process called double thresholding where you basically set two thresholds, um like a lower threshold and upper threshold. Edges that are lower than a lower threshold are just removed entirely. Edges that are above the higher threshold are kept. And for edges that are in between, you only keep them if they're connected to an already strong like edge basically. And that's literally it. So like for the purposes of this, I implemented it from scratch for you guys. So with the help of GPT. But here's counting edge detection, right? So like this is the blurring step I was talking about. You have a Gaussian blur, and then you compute like the gradients in the X and Y directions, like the strength of like the changes, like vertical edges or horizontal edges for every single pixel, right? And I compute the strength of it by taking its magnitude, and I get the angle by looking at like the relative strength of its X and Y gradients. And then I apply no maximum suppression, which is over here. So basically for every single pixel value, I check to see if it's the maximum value in its kind of neighborhood, like bottom left, bottom down, left and right. And I only keep it if it's the highest of those four values. And then finally, I apply double thresholding, where essentially I do it slightly differently here, but basically I just first classify all the points I have in the previous step as strong edges, weak edges, or anything in between. And then I use connected components function of CV2 to basically you guys know what connected components are, right? Kind of. It's like if you have a graph, like or a bunch of edges, right? A connected component is just a bunch of edges that are like adjacent to each other. So I take each connected component, and if there exists a strong edge in there, then I know that any of the weak edges in there like should be classified or should be kept in basically. So that's what I do. So if any of them have strong edges, then I keep it. Otherwise, I like just throw it out. And it turns out and as expected, right? Since I just implemented counting edge detection, like this kind of works well, I guess. So here's our custom counting edge detection algorithm, and here's the one that's implemented by CV2. And it's like kind of similar. It's like not as good as the like official implementation, obviously, because it turns out for double thresholding, I just set like arbitrary like values of forget 128 and or no 30 and 35 and 70, but like it turns out like CV2 does some extra pre-processing step behind the scenes, which makes it look kind of better. But you can see that like it's like broadly like working this candy edge detection algorithm. But okay, cool. Um, Next slide. And like this is kind of the last section of this first section, I guess. Histograms and thresholding. So this is something else that some people use in their take-home challenges. So like moving past histograms for a moment, thresholding is basically a technique where for every single pixel in your image, you like either keep it or you like you throw it away based off of some threshold, right? When it's like a single threshold, it's called binary thresholding because it's an on or off sort of thing. Um, and the reason it's useful is because again, images are like really highly dimensional and like you want to throw out as much data as you can while keeping your tasks sort of manageable. And like sometimes in trying to like decide the right threshold to threshold at, it's useful to look at the like the distribution of intensities or the distribution of whatever you're trying to threshold by. So like for example, during the challenge, you might have thresholded by, I don't know, like the RGB value. You see like what value of green you should like put the background off at, right? Um, so like for example, here's like another image, right? Where we're trying to get or trying to tease out like the images, right? Or like the edges and remove the backgrounds, right? So like something that you might do might be, oh, let's graph out like a histogram of like the intensity values, right? Um, and like, does somebody want to, oh, this is probably too small. Um, like given that this is the image and like this is the histogram, like does somebody want to tell me like what pixels correspond to like this insane like peak up here? Background? Does somebody say background? Yeah, it's a background, right? And like it all makes sense, right? And then like on the dark end, like the stuff here is probably like the darkest parts of this image. And then there's like a pretty uniform amount of like some lighter stuff, which might be explained by like the color of the building. So if you're trying to thresh out the background, right? If you want to just, yeah, take out the background, make it black, what threshold value would you guys choose based off this histogram? Yeah. Yeah. So let's try that out. So you just CV2 that threshold. I don't know what I put here, but let's do 2 times 2 suggestion. And yeah. So like setting 210 like as expected threshold just threshold it out the background. Um so these are two things I'm going to talk about in a moment. And you guys also use it in your take home challenge, but I'm not sure if you guys like understood it completely. So I'll just go through it now. So like three main techniques. Global thresholding is basically when you take my binary thresholding thing I was just talking about and like basically assign it to multiple classes. So instead of just having a single cutoff value, you have multiple cutoff values, and then for every single pixel value that's in between each like threshold, you assign to a different class. In the case of binary thresholding, there's just two different classes, so we assign it to like black or white, but obviously you can extend that further. With adaptive thresholding, the thresholding value becomes a function of a location. So instead of having like a global binary like cutoff value that you apply for every single pixel like equally, you maybe have like, as I said here, like maybe like you make the threshold like the average value in like the 3 pixel neighborhood of a pixel. Yeah. And then there's a more like advanced technique called Otsu method where it recognizes that or it proposes that pixels that are in a class are like um I guess like similar to each other. So like it will propose like a certain number, like you give a number of classes that you want, and it'll try to find threshold values such that the variance within each like group is like minimized. Right. So in our example here, um, like if you give Otsu's like algorithm like a number class of 2, it'll basically try to find a threshold such that in each of the 2 classes that you get from the thresholding, the variance within each like class is minimized. Does everybody know what variance is? It's like it's like the expected difference from the average value you have in a set. So minimizing the variance means that all the values in that set like is not like spread out. It's like very concentrated essentially. Like, there's no surprise on what the values would be. It's like there's if I put the threshold at 200, um the variance of the stuff on my right hand side would be like very minimized, right? But as a cost of that, like anything less than 200, like that class has really high variance, right? Everything's kind of like spread out smoothly. And so Otsu's algorithm wouldn't really like that. And that's the reason for which when I apply Otsu thresholding, the threshold defines is in 200 by 133. It kind of decided that at this middle value, like the variance between the two classes is like minimized, and that's what it went with. And this like kind of the thresholding I got. And like with adaptive thresholding, like I just put it as an example, like I think I made it like I really forget. Oh yeah, it just takes the average of like the threshold is the average of anything within like a pixel plus like some constant that you specify, and like I think I put 11 or something. But yeah, this is thresholding. I think that's it for the notebook for now. Okay, cool. And so on to like our second section. Oh, any questions by the way? Yeah. I don't know. It's been there for like a long time. Or actually, no, was it here last week? I think it's funny because only that one also has a yellow thing, but so I don't know if it's like a projector thing. Anyway, probably fine. I can like, yeah, it's fine. Um, okay. So next section, section two, um, cameras and calibration. So this is like really important for us, and this will be more math heavy. Um, how do I want to go about this? Okay. So like a quick overview, and then I'll dive into the math a little more. So like with so like everything in C computer vision, like basically, or most things kind of boil down to this like pinhole camera model, which is the concept that your camera or your source of information perceives a world from like an infinitely small point. And like what do I mean by this, right? Like let's say that I can't even see my cursor. All right, let's say that this is your camera, right? The idea is that like everything like, and this is a tree you're trying to take a picture of, like it's just saying that like all the things and like all the light that it receives like comes to the small point. So essentially like it basically abstracts away like um any like distortion or anything you might have in real life, and just assumes that your camera just takes whatever it sees in real life and just records down in 2D like a skilled version of it. Right. And obviously there's some sort of like dimensionality loss because things in real life are 3D, but cameras measure something in 2D, right? And so like what this model does is that it throws it just the dimension it chooses to throw away is basically like depth. Right. So a tree of height 5, which is just 5 feet away, will look exactly the same as a tree of height 1 that's 1 foot away, and that's something it's willing to live with, right? But like despite like this drawback, um, or like it's not really a drawback because you have to live with it when you're like decreasing dimensionality and information. But like with this model, like you can do some pretty cool things, right? Um, let me just go into the notes, uh, like for more detail. Or actually, I can draw it out probably. So so like first of all, there's a concept of like image coordinates and or pixel coordinates in your image coordinates and pixel coordinates in the world, right? You have P of camera, right? So let's say you have like a person here. This is in real life, and then this is what your camera sees. It's like a smaller scale version, like that the camera sees, right? The idea is that every pixel in this image is mapped to like its corresponding point in real life. And what we're interested in as computer vision people is like getting them like mapping each pixel in here to like real life, right? Because what we see is a camera, but what we want to do is in real life. So we want to map basically pixels to real life coordinates. In other words, we want to convert from a picture of camera to picture of world. Or I don't know what pixels to pixel world. That's just what we're interested in. And like with the model I just described, where like anything that you perceive in real life is just like a scaled version, or anything you perceive on an image is a scaled version of real life. Um, let me put some variables so that you guys can like make this like a possible problem. Um, so like let's say that I already give you like the depth, see, and this is really important because this is the stuff that the camera doesn't know. So let's say I already give it to you, right? And you know for a fact that this thing here lives at xc comma yc. Does somebody want to tell me like the 3D coordinates of this point, this exact point? Or is there enough information to even like decide what coordinate that is? The depth is z. And you like this one is xc comma yc. What is this one in real life? It's like well, what's the depth? Like the depth is obvious, right? It's already z. Okay. And we already said that this is just a scaled version of whatever you see on a camera, right? It's just like a linear transformation. It's like let's I mean, I don't want to give away too much, but like, okay, so let's say that, uh, hmm, like, did I give you guys enough information, or like, is this, is this all you guys need? From what to PC to PW? Well, that's what we're trying to like derive, right? Um, well, I know, but like, I'm saying like, given the information that you guys have, like, is it possible? Like, what, like, if I were missing something, like, what do you guys need? Uh, oh, well, what is the focal length? You're kind of getting ahead, but Yeah, yeah, it's the ratio. That's kind of head, but I mean, like you can like okay, okay. So the focal length is basically it's like the ratio between like a point on the image and like real life, right? Um, so like I'll just give you guys the equation actually. Yeah, I think it's one sec. Okay. Okay, so F, do you want to explain what focal length is or like the concept? Like broadly speaking, like what does it mean?
But I just know the ratio between F and the D. Uh, uh, it's just the ratio between the X camera and the X orb. Is
Okay. So like actually like the most precisely, if we go back to like the model of like the pinhole thing I was talking about, right? Like what I'm missing here, actually, I was hoping you guys would like remember what I was saying earlier, but basically like there's a pinhole, right? Everything you see is like projected through a point. So like actually this image should be upside down. Um, I mean it's like right there, but uh so like I guess it's not that accurate. Um, so at this point maps to this point maps to this point, and like I know this point maps to this point, like it like they all go through this pinhole. And the focal length, F, is defined as like the distance between here to here. The distance kind of from like where your pinhole is and like where your image like fully like is defined. So like when you take a camera, right? Um, or like it sort of measures like the intrinsic like scaling factor that your camera applies to whatever it sees in the real world. Um, and then so like this was like kind of the information that you guys were missing. Because without this, you can approximate, right, whatever you see in real life. You know that like PC or like the distance you know that y of w like over y of z or sorry over y of c is always going to be equal to x of w or x of c, right? You know that like this what the scaling factor is always going to be the same, but you don't know like exactly how much like to multiply the scaling factor or like what the scaling factor is, right? But like actually based on like the linear model I've told you guys, like you guys see why this is true, right? Um, and this is exactly why like if I'm like a 5 feet person standing 5 feet away from the camera, looks the same as like a 1 foot person standing 1 foot away from the camera. This ratio is the same. Um, okay. How much time do I have? Do I have time to go into like? Oh, you have time. Okay. Um, shoot. Can you tell Kevin where we're meeting today? Kevin's song. Wait, is Kevin here already? Where you're Kevin, right? Oh fuck. Never mind. Okay. So, okay, cool. So like, basically, with this focal value in play, and I said it was a scaling factor, right? You know that any point on your image, PFC, or PFC, which is equal to X of C, Y of C, right? You know that X of C is equal to F times X of W over the depth, right? And then you know that the 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 image, the image height. Can you guys see this? You know that Y of C is equal to the focal length times the world or the world of height over the depth, right? And like confirm that like these two equations still like maintain like the invariance that we had before. It's like he's right there already. Cool. Okay, cool. So this is kind of like the basic, like this is kind of like the main thing I was talking about. So like um we're like computer scientists and like we want to like, you know, implement things in terms of like matrices. Oh yeah, and one thing I forgot to mention, usually people like add like a constant c of x and a constant c of or c of y and a constant c of x because like we need to like have a coordinate system in place. So like some people like your image is like a grid or it's like a square, right? You would just maybe like force it to be 0, right? So then you just add an offset to everything that you define. So like make sure that your image is like has an origin point and everything like stuff like that. So like this is our like kind of final like sort of formulation for like to converge it between like image points and wall points, right? And it's like in an effort to try to like express this in like a sort of a matrix transformation, so that our computers can like compute these sort of transformations like efficiently. Um, let's say that I had, let's say at PW, and I want it to be equal to, you know, x of w, y of w, and c of w, and then I have p of camera, which is equal to x of c, y of c, and 1. Right? Do people see why I put a 1 here? Because like camera coordinates are in like 2D, right? Like why did I put a 1 for the z-axis and why does that make sense? Yeah, we're just normalizing it, right? So like as I said, any image coordinate can have any arbitrary like they're all the same, like off by a scaling factor because it's 2D. So like just for principle, you can put whatever you want here as the last value, but we just set it to 1, just like to have a baseline. Okay, but cool. And I want I'll keep this equation here so you can have it as reference. Handwriting's bad. Okay. Let's say that I want PSC to be equal to some matrix M times P of W. So you want to like propose like some M's. Like what M would work for this configuration? Okay, let's just use variables, yeah. Like first of all, like what is the dimension of this guy over here? Is it 3 by 3? Okay. Um, we know that XC is equal to F over Z times XW plus C of X. Okay, nice. You said somebody said 0. Okay. What's the last one? CX over what? CX over what? Yeah. Yeah, CX over 0. Well, what's one here? Okay. F over Z still, yeah. And then what? F plus dy over zy. How about the last one? Yeah. So like the last one is kind of like freebies. Like you can just sign up to like whatever you get. So yeah. So like it turns out that you can like if you and like it turns out that you can decompose. If you look at the screen, right? This is our M. It turns out that you can decompose it into like a rotation and a translational component because if you think about it, right, as you're moving as they're moving from like world to image, right? Do you ever like if world coordinates are like here where the origin is, and your image is like over here, there's like a translation and there's a rotation, right? And it's like it turns out that the matrix came up with can always be decomposed into like one dimension. I like derive like the more simpler version, which is kind of mapping 2D to 3D, but most people in like the industry and the academia actually add the one to like the 3D world coordinate and make the world coordinate like X, Y, and Z. Or make the image coordinate X, Y, and Z. So like it's like different. And the reason they do this is so that your rotation matrix becomes like a nice like it becomes part of SO3, which is like the class of rotation matrices basically. Um, but yeah, that's kind of it. And like just kind of recapping what I just went over. Um, so in this like transformation, right? You have uh kind of like five sort of main factors that affect this computation, right? Number one, which is the focal length, which I just mentioned. Next is the optical center. So like kind of where you set the origin to be in relation to the world. And then like lens distortion, which I didn't talk about. Is would lens distortion, do you guys know what lens distortion is? Okay. Okay, we'll skip that for now. I'll go over in the next slide actually. And then apart from that, so like these three things are all things that are a factor of the camera that you use, right? And then the other two things, extrinsic parameters, would be the rotation translation vectors. These are things that you impose on the world. You impose based on your view of the world. And then like again relating to CV2 because that's what we're using. You can use CV2.project points to go from world to image. And how would we go from image to world? The opposite. Yeah, multiply inverse. Pretty cool. Yeah. So as I said before, so like, all right, you guys see my cursor, right? So these two things are what? Extrinsic parameters, and this thing is what? Intrinsic, right? And then so when we're trying to calibrate our camera, which one can we calibrate? Yeah, right. Because RNT is something that we set based on our view of the world, right? K is something that we're not sure of. So K is something we have to derive whenever we're working with a new camera, whatever. Even if the manufacturer gives you like an intrinsic matrix, right? And the reason it's called an intrinsic matrix is because it composes of the intrinsic parameters that are useful to us. You should still like measure it yourself because there can be manufacturing defects, etc. So onto lens distortion. Lens distortion is it's not even presented. I'll just go here. This sort of thing, right? When there's like you would have maybe seen fisheye lenses or stuff like that. And like I guess going back to what I was just talking about, like would the lens distortion coefficients be part of like our intrinsic matrix, rotation matrix, or translation matrix? Which matrix would it be in? Okay, that's kind of a trick question because again, as I said, rotation and translation matrices aren't something from the camera is an extrinsic parameter. It's something we define, right? So it definitely be if it did exist, it would be in the intrinsic matrix. Now, would it even be in the intrinsic matrix? Based on the equations that we had before. Like would distortion even be in the intrinsic matrix? Is it even possible to encode it in the intrinsic matrix?
Would it just be like a scaling measure?
Okay. Short answer is no, it's not in the intrinsic matrix. Long answer is like kind of yes. You can like sort of approximate distortion. But the issue, like based on like whatever current pixel location you are in the image, but the issue, like the main reason that it's no is because our pinhole camera model is a linear model, right? It assumes that everything is like just a exact scaled version of your like world coordinates. So like distortion is something that treats pixels differently like depending on where it is in the image itself. So that like pinhole and like scaling assumption breaks up pretty quickly. So like what people do is that if your camera has distortion, which every camera in the world does, unless it's like I don't know like made like really precisely or something, is that you somehow, and we'll go over this today as one of the tasks where you guys are going to calibrate your own cameras, but you're going to like get the intrinsic matrix. And then based on the intrinsic matrix that you can best approximate, look at the difference between the projected points based on this linear model and the actual image that you get. And then through some algorithm that I'm not going to go into, you're going to be able to like kind of approximate like to what effect the distortion is. And then whenever you convert from world to image, you'd apply your intrinsic matrix times whatever you set RNT to. And then on top of that, apply your distortion effect. Yeah. Oh, you no question. Okay. Um, cool. And then so like going to a little more detail on what distortion is. Oh yeah, I put it there. I forgot. It's like the issue is that pinhole camera model is linear, right? So it can't account for like any radial or tangential distortions. And then so how we fix it, you apply these distortion coefficients and then you like their functions in CV2 that allow you to like reverse or apply these distortion effects. So like how do you calibrate, right? Like there are these like things, but like how do you even like calculate these, right? And that's what camera calibration is, right? And I said that it's important because you know your camera isn't perfect. You want to obtain accurate measurements. You want to like map from what you see in the image to like your model of the world well, because like if it's not accurate, then any downstream algorithm that you apply to your world coordinates will like mess up. It's like I have some tech. I have like a technique up here, but like just from like a first principles point of view, like if you're trying to like figure out what K is, like how would you do that? Like there are like three equations at play, right? There's PC, all right, there's PW, and in the middle we have like some K matrix. Right. How do we calculate K? Like what do we have control over? What do we have control over? RNT, okay. We have control over RNT. What else do we have control over? Okay, well if we have control of RT, like these three things are kind of tied together, right? Because if we have a set rotation and translation from our worldview, then the pixel world coordinates are already fixed. Like we already decided that. So these three things we have control over. What do we not have control over? Okay, PC, right? PC is what our camera observes, right? Like we should be able to solve for K, right? So what usually happens is that like your camera sees a bunch of points, right? And then you use your knowledge of the world. Like let's say you want, like we have a chessboard in this example, right? Let's say you want to create a world model such that each grid, like such that like you want this to be 0, 0, you want this to be like 0, 1 or 1, 0, and vice versa, right? So what I've done now is essentially I've established, I know what this is based on the image itself. And I've established this by just, you know, arbitrarily assigning my units, right? I want this to be at 0, 0, 0, etc. Right? And I could just solve for K, right? If I want, you guys see like the relationship between this? Okay. And so like in practice, what happens is that, well, I'll just like go through the script. And this is what you guys are going to be doing later. But you'd capture some calibration images. You'd like set what you want the world coordinates to be. And then like you let CV2 do the rest, basically. So let's look into that. More calibration.py. So I've written like basically all like the hard part of the code for you. But it's the setup of the code for you. But basically what happens is that you want, so like we have a chessboard, right? CV2 has this function called like find chessboard corners. We're given an image of hopefully some chessboard. They'll return to you the image coordinates of the chessboard corners. They'll do all that for you, right? So CV2 will handle this part for you, right? So all you have to do is to decide on some sort of like world system. You can assign however you want. I would recommend to keep things simple, you know, you can make like the bottom left 0, 0, like vice versa. But then you decide this. So right. So now you have world points and image points. Right. And then you just call this calibrate camera function. And what this will do is that it'll spit out a K, which is your intrinsic matrix. And I believe D is the distortion coefficient, are the distortion coefficients. Does anybody have any guesses for like what these two blank spots are? What are the two things missing that I haven't mentioned yet? Rotation and translation, right? So, um, so cool. So these two blank spots are rotation and translation. Now, second question. For each image that okay, so like we feed into Calibrate Camera like a series of points and a series of images, right? And like for more context, this is actually for every single image. Like, so you feed into Calibrate Camera like a bunch of like different images, right? Because like sure you can approximate K just from a single image, but for more accuracy if you like feed it a set of images. Basically you just want multiple point of views for it to like be more accurate. So like essentially image points would be for each image, what are the chessboard coordinates? And world points would be for each of the images, what should the world coordinates of the corresponding like chess coordinates be? And it's like for our purposes, world coordinates should just be the same set of world coordinates that you've set, multiply like fit into like 8 times if we took 8 images or 9 times if we took 8 images. And image points should just be whatever like the 8 sets of coordinates that CV2 the affine chessboard coordinates gives you. But yes, so now on to my question. What dimension is R and T? Is R just like K in a sense where um R is like some matrix, or is it like image points where it's like where its dimension is like number of images by matrix? This is a little hard. I didn't get it the first time I saw this either, but I mean just 50-50, right? Let's make a guess. Okay, raise your hands if you think it's like just a single matrix and that's it. And everybody else thinks it's like the latter. Okay, well, let's like work through step by step, right? So I was actually like misleading you guys a little bit by saying there's a single K. But recall like what I said, right? For each set of image points, we have a corresponding set of pixel world coordinates that we feed to it, right? And given the fact that the world points that we feed to it isn't consistent across set of frames means that what? Like, sorry, I phrased that badly. Like, calibrate camera doesn't expect the same world coordinates for every image you give it, right? Otherwise, it would have just asked you for like the 8 points of the chessboard corners and like just apply at the same ones for every single image, but it doesn't, which means that it's okay with each image basically corresponding to like a different set of points, right? You can have one image be be a picture, like you can have one input be like an image where you map world points of like a dog to like the image of a dog, and the second picture could be like the chessboard example, and the third image could be something else entirely, right? Which means that it doesn't expect all of them to be the same, right? You have a different mapping for each. So for each image, you have the same camera. It expects the same camera, but it doesn't expect the same transformation from world to image. It doesn't expect the same RNT, which means that for each of the images that you feed to it, you get a different rotation and translational matrix, depending on the point of view you give to it. Which is why when what it returns for RNT is like actually a set of images or a set of rotation and translation matrices for each image, right? And why do we throw that out? Why do we not care about that? Or why did I throw it out? Right. And there's a stupid answer and there's like a more like nuanced answer, and both are correct, but who knows the stupid answer? It's like kind of obvious. Okay, well, we're just trying to find K, right? Like I don't care about R and T. So I just threw them out, which is valid, right? We're just trying to find an intrinsic matrix. And the more nuanced answer is that we specifically don't care about the R and T for every like image like we give it, because this is something that we control, right? So in any downstream task, like I can set this to however I want. What I just care about learning right now are the intrinsic parameters, the stuff that I can't control and the stuff that I don't know about. And so I could keep the RNT, and then it could give me a perfect mapping between whatever input images I give it. But for my purposes, all I care about is this K. And so yeah. Uh, Hopefully that makes sense. Any questions? This took like for me some time to wrap my head around. So like I'm surprised you guys don't have questions, but yeah.
So A is like the linear intrinsic parameters. And
Yes.
D is like the distortion.
Yes.
Not linear.
Yeah. So like what I'm keeping, and yes, again, distortion. What dimension is it? What do you guys think? What dimension it is? Is it like rotation and translation where there's like a different output for every image that you feed it depending on like the mapping, or is it the same as K where it's just constant for everything? Yeah, it's just like K, right? It's an intrinsic parameter. It doesn't change. Like no matter what image that you give it, like the distortion is going to be the same because it's the same camera used. I mean, CV2 is making an assumption that you're using the same camera to capture, right? Obviously. So yeah. D is also gonna be like one single matrix. But R and T are they're gonna change with like whatever images you give it. Okay. And so like this, you guys will do this like later. But see how am I doing on time? Okay, not bad. I should probably speed up. Okay, so next section, I think. Um, feature detection and matching. Um, okay. Have you guys heard about features in the context of like learning and like machine learning and stuff like that before? Does somebody want to like explain to me what features mean? Like what do they generally mean? Did I cold call? Okay, you first. Like-
I guess like just in the context of like,
Any context, like where have you heard features?
I guess it could be like stuff that you can characterize and quantify in a specific.
Yeah, that's actually a really good answer. So like features are like okay, how about this? The reason we need features is because in most problems that we have, in any like ML or CV problem, like we're trying to approximate some like world model, some model of the world. But the our inputs are like too high dimensional, right? Like they're like usually intractable. Like when you're trying to like model like physics, for example, like uh image detection, like your input is actually provably intractable because there's not only what you observe, but also like the stochasticity of like the I don't know the universe, and there's some randomness inherent. So you have to like through some measures like extract information out of these inputs into what people call features, right? And so in the context of I don't know, image detection, maybe a feature could be or sorry, that's a bad example. In the context of like house pricing, right? That's a famous one. Like input space would be all houses in the world in all perpetuity, right? That's obviously impossible. So like what people do instead to like abstract down the feature set or extract down the input space is to like have features like how a square feet. That should be like a useful input. Or like I don't know, location, number of stories, stuff like that, right? Those are abstractions that people use heuristics to um make the problem easier, right? You're recognizing the fact that most information out there in the world probably isn't that useful, but these 4 or 5 things I'm using to train my model are like the most important or like the best that we can have, and they're good enough, right? So that's what features are. In the context of computer vision, and when you're dealing with like a video feed, what would features be, right? Our input space are what? A set of images, a set of pixels. So what would features be for any like arbitrary downstream task, or maybe not any arbitrary downstream task? Let's say like you're trying to like you guys know optical flow. Um, you know, explain what optical flow is, like broadly speaking. Have you just heard of it?
Trying to match like feature in one image, how it's moved between two.
Yeah. So like,
Or-
yeah. So like let's say that you have a plane or a drone, right? Like in the kitty world, right? Like your camera is like constant, it's not moving. It's the things around there moving. But in the real life, when you have any agent, like the camera itself is moving. And so like the goal of optical flow is the assumption that like given that you know something about like your target image, based on like how it changes, how your perspective changes, like kind of guess how R and T are changing, right? That's what optical flow is. And like what features would be like useful in trying to estimate R and T through time in an image? Like obviously, like okay, I guess to abstract it down for you guys, like let's say I was like you guys need like let's say I blindfolded you guys, right? And like let's say all you guys saw was like an image, was like completely black, right? What would you like? And given that you saw like one frame initially, at what points would you like poke out points out of your blindfold to like what points will most optimally allow you to like guess like what how you're moving around? In other words, like let's say like we have this like graph for example of the house. Let's say that the first frame that you saw was this house and that you're moving around but you're blindfolded, right? Like what pixels would you choose, or what set of pixels would you choose that would like make like guessing your movement the easiest? And like let's say you're trying to minimize like the amount of pixels that you need. Like maybe starting from easy. Would the background be useful information? Would you want to like see the background? Okay. So that's like I think so in contrast, what would be useful when you're trying to like guess like how you're moving throughout? Like what are certain features? What landmarks? Like let's say maybe this is not a great example because like it's so big, but like let's say that let's say they have some like landmark, right? Let's say that you see the I don't know, the Statue of Liberty. Like, what would be like a good location on it to like kind of ground your things around? Eraser. The torch, right? So in terms of like, even in humans, like the regions of interest are usually like the edges. Edges help a lot. And everything else kind of doesn't really matter. So like a useful feature for downstream tasks could be like edges, right? Like abstracting that even further, let's say you're trying to like detect edges, like what are like what's like one aspect about images, like you have like the entire image and you have edges, like what's like one layer even further down that's even more useful. Is that kind of hard? Like, oh, go. Yes, corners, intersection of edges, right? Like I don't really need all the edges. If I need the intersection of edges, that tells me information about what? Potentially 2 or 3 edges or even more, right? So usually with key points, like everybody's basically just trying to find like corners in an image, essentially. But you have to be smart about it, right? Like for example, in this image, like this is a corner, mainly because the stuff around it is mainly white and there's like only a little bit of black. But similarly, like at this exact point here, this part is mostly black and this is only white, but this is obviously not a corner. So you have to do some smart stuff about it. Wait, going back, so like this is what features are. Like key points are distinctive points in an image that are useful for like image matching or tracking or like whatever else that you might have as a downstream task, right? And so like just to name a few, like downstream, like or actually before I name some algorithms, we can go to the next slide actually. You also want feature descriptors, right? Like let's say like for a given image, like you're able to get like features. So you can be like, hey, given this image of a house, these 6 points are features, right? What aspect am I missing if like say you're doing optical flow and you want to find how things change through time? Like I've right now for each image through time, I have 5 or 6 points. But like they're changing perspective, right? So like what do I need to like complete the picture, essentially? Like what information is lacking? Yeah, one more time. Okay, so like let's say that I like you're like looking at this house like through time, right? And you apply the same exact algorithm onto your point of view, and like maybe in the first frame you get 5 points, the next frame you get 7 points, right? The next frame you get 5 points again, 6 points, 4 points, right? Like, and I wanted to do optical flow. Like what? Like I already have the points, but like what? Like I don't want to. I don't want to say the answer without giving it away, but like what am I missing to like be able to like connect these points together? Yeah. Yeah. You want to have sort of like function that maps any candidate key points across images, right? We don't want to just have the ability to like find useful points in image. We also want, most importantly, the image to like connect them together. Because if we have the points but we can't map them, like there's no point, right? So like that's why you have things called feature descriptors, where basically like for each point, like you or for each key point rather, you like assign like a description, like a feature vector that kind of describes what it is. And then when you're trying to map features to features, like from frame to frame, um, like most people do, like they just maybe take the cosine simulator of the feature vectors. Like there are ways to like go about this, but in that way you're able to like align key points across frames. And then like once you have like a mapping of points, you can apply your RNT and your K matrices, or you can apply your K matrix, find out RNT, and then you can find out how RNT changed through time, right? Because the key points would be POW, right? Or no, sorry, my bad. The key points would be P of C, right? Based on it. So the key points could be P and C, right? And you basically get delta of P of C, of PC right now, right, through time by matching the key points. And you know K already, right? And you know POW. POW stays constant. Like let's just go with the assumption that the building is like rooted in place. So you know POW is constant. So like we know this, we know change in this, we know this, and we know this. Then you can find change in this, basically. You can find how rotation and translation matrices change through time. That makes sense, right? Okay, any questions? Okay, cool. So like as I just alluded to, like there are like kind of 2 parts in features, right? You have a feature like detection and like retrieval phase, and then you have a feature descriptive phase, which both of which are like equally important. So because you want good features, but you also want like good ways to describe those features. So SIFT. The astute among you may have realized that SIFT appears in both of these slides, and that's because SIFT has both of these aspects. And it's probably like the most widely used one. It's the only like it's the most widely used one because as the slide says, it's scale, and rotation invariant, right? Which means that even if your perspective like rotates or like zooms in or out, like it's still able to detect features. But a drawback of it is that it's like more like computationally expensive. And I think it's best to like display let me see. Go step by step in the algorithm. It's kind of involved, but it's not that bad, but I'm also not that confident because I just like reviewed it this morning. But on the right, oh, none of you guys went to the flight test this morning, right? Oh, Brandon did. We flew the plane. You guys see? You guys saw the video? It did not crash and burn. It had a majestic send off, and it landed too in one piece. Okay, anyway, so I'll just like go through this. I'll just give you like a high level overview of this Wikipedia article. Okay, cool. So it's not useful to us. Wait, hold on. Oh, here. Okay. So first of all, like what this algorithm does is that it applies a difference of Gaussians. Okay. Gaussian has some what? Gaussian filters. So basically it applies a bunch of blurring filters to the image, right? So as I mentioned before in like the third or fourth slide, like we have blurring kernels that blur the image. And so what this is doing is that it takes a kernel of like maybe size 3 by 3 and blurs it. And then maybe it takes a different kernel of size 5 by 5 now, and then blurs the same image again. And then maybe a 7 by 7 kernel, and then blurs it again. Oh, is there a reason why most kernels are like odd dimensional, like in terms of the go on? Yeah, you need to have a sender, right? You could like they're like approximations. Like you could technically use a 2 by 2 kernel, but it gets weird because like each point that the 2 by 2 kernel outputs doesn't really map to like a point on the original matrix. It'd map on the point to a point in between, which could work, right? That could work, but most people don't really do that. But anyway, yes, we're checking a difference in Gaussian. So like as so you can think at high level, you can think of this as like basically like applying increasing blurs to your image and taking a difference, right? And as I said before, and this is the concept that I said would appear later, like it's useful to keep like blurs are useful because key points come out after you blur them. And so like this takes this idea like even further by saying, hey, key points are important, appear even as you increase the blurring effect, right? So this is just saying that we first take points that appear even under like the difference of Gaussians, like under like the delta of blurred images, basically, of increasingly blurred images. And this is what we get. Through that first step, you get this first image, right? And like let's say that you had this first image. What would be the first thing that you do to like clean it up? Oh, why should I give it away? What would you how would you clean this up? You guys saw the answer, just like say it. Yeah, you remove the background. How would you remove the background? How do you know if a given canon is a background? Wait, I should cold call. Let's start from there, back there. Oh shoot, I'm so bad with names. What's your name again? What's your name again? Huh? What? Oh, Demetrius. Okay. How would you remove like these extraneous points? Okay. What would you throw? Let's say you had like no aggregate information about the picture. Let's say you only had information about what was like nearby the pixel. Yeah. So like you would remove pixels that are what? Key points, kind of the key points are what? Where they're yes, where like the pixels around it are like the same color, right? That's the first step. And so that's what they call discarding low contrast key points, right? They discard that. So that's the first step. And then the second step is oh, okay. Like basically like they remove edges by like finding the curvature which they get from like the Taylor expansion. Like wait, do people know what Taylor expansions are? Like basically like polynomial like approximations of like an intractable like function. So like our difference of Gaussians was intractable we take the second order Taylor expansion to approximate it, and then we take the second derivative, which is useful because what? In this context, why are second derivatives useful? They give you curvature, right? Concavity. Anybody took BC? Second derivative is concavity, curvature. So we take the second derivative to find where there are curves in like the gradients, right? And then images, and we want to remove edges, as I said. We don't want edges anymore. We want the intersection of edges or corners. So would edges have high or low concavity? Low, right? Edges are exactly the points usually in our world, in this human world. Our edges are points where like there's not that many curves. There's like a straight line. So use this approximation to like basically remove edges that or remove the key points that are edges. And it kind of works, as you can see here. So you clean up even further. So now you have a bunch of candidate key points. Okay. Blah blah blah. And then you assign orientation. And why do we assign orientation? Am I in the key point detection step or the featured like vector step for this part? I think the person who wrote this Wikipedia is actually like a little wrong here, actually. So like I think orientation assignment is actually a part of the key point descriptor set like section, right? Because we've already like found a candidate set of key points. Now we want to like assign features to them that allow us to like map them even in between frames. So like part of that includes orientation, right? Relative to like our main like image, like what is the orientation of this key point, right? Okay. So like they do it through some math. I'm not gonna go into it. Blah blah blah, and that's kind of it, right? And then like secondly, like in addition to like orientation, they also like encode like the identity of each key point by kind of like what's in its neighborhood, right? So like if you read the article, you take the 4 by 4 pixel neighborhoods, like you bin it, and you get the magnitude and orientation values of samples within it, blah blah blah. Okay, how would you actually no, this is probably too hard. So like basically they like map like features across frames, but I think using some like binary tree approach. I don't think they talk about it here. Like or like k-nearest neighbors actually. But there are like many ways to do it, but like essentially there are ways to like basically map vectors close to each other through KNN or like cosine similarity or whatnot. But this is fit. Brief. This is I skipped a slide, didn't I? Actually, I don't think I have time. Like just like um briefly go over these concepts. What was like can somebody tell me what would the drawback of scale SIFT was? Ah shit. You, what's your name? Arjun? Yeah, what was the drawback of SIFT? Okay. And based on what I told you, like what step in that process was the most computationally expensive, perhaps? Kind of. Taylor expansions are actually quite efficient these days. What other step might be like considered computationally expensive? You have the blurring, right? Because you have to for the whole image, you gotta apply the kernel, and like a bunch of different kernels. That's really expensive. Um, so that's something expensive. On the feature descriptor end, like what might be expensive about that? Like in general, like in still you. I mean, I would just straight up like it would be expensive because the features are too big, right? Like they're too high dimensional. Like I didn't feel like was reading closely, but like the features it comes out with are floating point values, and those are huge memory wise. So like what would be like a natural way to encode features differently? What's your name again? Yeah, Rochelle. Yeah, like how would you encode features? Like what other way other than floating point numbers? Like what is the most efficient way you can encode numbers? Okay, integers. Sure, that's definitely level like more efficient. Next, is there another way that's more efficient than integers? How do computers store integers? Yeah, it's bits. So like you can store um like the feature descriptor as like a binary value, right? And that's basically what brief does. Brief basically encodes like images or encodes these features as binary values. And how would you compare two different binary numbers in terms of similarity? This might be a deep cut, but anybody? Yeah. Uh but the input is two. Like I'm asking, like, given like two binary strings, how do you compare them? I mean, okay, it's just you just take the XOR, right? That's like some measure of like similar, because the X or what? It only returns one if the two things are same, right? And you just do it pixel by pixel. And depending on the value of the XOR, you get like a measure of like how similar the values are. So like that's what brief does. Brief just like through some like clever way you can read in a paper, it like assigns each key point that you already gave it from, whether through SIF, probably not SIF, because if you use SIF, then the computational gains you get from the feature descriptors are gone, essentially. But you can use fast, which is a different algorithm. Oh yeah, and what I don't want to. Okay, I'll talk about that in a bit. But basically, given the key point descriptor, it samples the points around each key point in a smart way, such that you get like a binary value for each, and then it compares features through like XOR. And like the bigger the value, the more common like the feature descriptor is, the pairs. Okay, fast. Fast is fast because it only handles corner detection. And like, does somebody want to like arbitrarily like tell me like what like how would you like detect corners? I'll start from this table. Kevin, you want to start? How would you want to detect corners in an image? Curvature. I want something faster. Let's say I want to only spend 5 points, or yes, 5 points to detect whether or not a given point is a curve. Or 4 points. Yeah, 5 points. Yeah. Let's say like this one is a corner, right? You would agree, but this one isn't a corner, or this point isn't a corner. Like, what's different? And let's say you can only sample the same 5 points around each candidate corner location, right? Well, how would you place those 5 points like in a smart way? If yeah. Okay, next one.
Have we already done that in detection?
Yeah, I actually already like said the answer to this question like earlier, but I don't know if like everybody was listening. But like, yeah, how would you like detect corners? Okay, and then what? We don't know anything. You go and you can't don't you can't draw a pentagon. I don't even know what that means. Like you can only sample 5 points. Yeah.
I would just sample of 5 points and
Okay. And then and so you get like 5 pixel values, right? 5 colors. Then what do you do?
If 3 of them are like similar and then 2 of them are similar, we have 2 groups, so
Okay. Yeah, that's kind of what I'm looking for. Like basically like if most of the points are like, well, they're like some counter, you're close. There's some counterexamples though. Like for example, like this point that's in the border, like not a center, like you can like have 5 points that like fit your description, right? Like, so what's one key thing that you're missing? Kaylin. Oh, as a center? Oh, is that what you said?
no, like you have
Oh, but no, yeah, but that's correct. Yeah. Yeah. That what you're missing is a center point, right? You want to know the value of like the pixel you're currently at, right? Like a bunch of points near like the true edge, either true center, what's that for a condition? Like only one point's the true edge or the true center. And that's like, so like, which is why it's important that like you have like the pixel value like itself. And so like basically what fast does is that like 5 is just like a very bad example because like it's only sound enough, but I think they use 16 or something. They take 16 points around like any candidate point, and then so I'll just hold the paper. But like there's like they make sure that basically most of the points are like different from the either most of okay. I forget it a little bit too, but let's see. I think they had a good like explanation here. Yeah, so they sample a bunch of points around it. And then and like here's like the condition, right? They look at the intensities of pixels. Like if the pixel of your current point, if the pixel like okay, so like they consider, and the one thing that the final thing that we were missing is like we want to we want like continuous points, right? We want the intensities of or the colors of the pixels to be like the same. There needs to be no breaks, right? So like so you select it for every feature point. You have like these three states. IP arrow X is basically like for every contiguous segment of points in these 16 samples, like if there exists a contiguous segment of pixels, you make its intensity like whatever that is. And if that value is less than your current pixel by like a certain threshold, you know that your current point is darker. The opposite case is like if it's brighter, and if it's not, then you think it's like whatever, right? And yeah, so like the third thing that we're missing is that we want like we have the color of our point, and then we have the color of like whatever like the background is, and we consider like a color of background if it's like contiguous, basically. Like that's like the high level overview. Anyway, so yeah. Or basically takes fast and like assigns orientation to it in like a more efficient way than like sifted. And now that since we have orientation for fast, we need to make brief orientation as well. And like and rotated brief is basically like we have like a binary string as feature descriptors. And what it does is like applies like a cosine and a sine thing to like all of it to kind of like rotate it to like a code rotations. So they're not binary anymore, but they're like integers, so which is like fine. Okay. I forgot what freak is, to be honest, so I'm not gonna go into freak. But anyway. Yeah, and then like feature matching techniques, right? As I mentioned, you have k-nearest neighbors, brute force matcher. Can somebody shoot. Let's does somebody want to like guess like or like if I give you like a bunch of like candidate feature descriptors or key points and their associated features, how would you like try to match them? Yeah, look at every pair. You brute force it. That's right. Which is what brute force matcher is, right? You like, oh shoot. You like compare every like pair of key points and see like which one's the best for each feature. But it's not as good because it's n squared. Like that's not super efficient if you're like doing anything that's in real time. So there's something called flan, which is basically like an approximation of nearest neighbors. So like the nice thing about this case about like because brute force matcher would be necessary when what? When our feature vectors are what? Like okay, let's say this. If our feature vectors were categorical, in a sense that we assign a class to each point, would it be like you guys can see like why brute force matcher is like the only way to like do things, right? Like if for every image we had like a set of unique classes, right? But like since we assign vectors and vectors like have like some sort of measure of similarity, we can compute in constant time. Like they're better approaches. Like for those of you who are taking 121 or have coded in the past, like you guys have probably looked at problems where like you should first sort the problem, right? Because the things are ordered, and then do like some sort of linear match. It doesn't make sense to do like to do brute force and compare every pairwise point. If there's some sort of ordering in your input, you should sort it first, and that's kind of what K-NN does. It leverages the fact or approximate K-NN does, right? It leverages the fact that your feature vectors are vectors, and you can compare them, so you can like first sort them and then compare them in kind of a greedy manner. But yeah, as I said, you need some sort of like, distance metric, and that could be Euclidean distance, cosine similarity. Yeah. Okay. Any questions, by the way? And also, am I going too fast or is this like fine? Huh? Okay, we'll see. Okay, awesome. Okay, ransack. Has anybody heard of ransack? It's kind of like a famous algorithm. For those who have seen it before, yes. Okay, yeah. Yeah, if you're taking like 580, you've seen it. So like, but ransack is like basically like I wouldn't even call it an algorithm. It's more like a framework, right? So like, it's a framework you assign to algorithms where you recognize the fact that your data might be noisy, right? And this is especially applicable to us because like this is our CV stuff is in real life. And it's like we like there's going to be incorrect matches from our algorithms due to whatever decision sinners may run into, and our data is obviously noisy like inherently, right? So Ransec is just an algorithm that like basically uses like SVD and like it randomly samples subsets of data, as I said. Runs the model that you have. It could be optical flow, it could be flan, it could be SIF, it could be whatever. And basically finds outlier inputs, or aka they try to be smart, call it inliers, which is basically a set of points that it thinks are good, or like in other words, it's a set of points that are consistent across subsets, are shown to like, contribute to your model parameters like importantly, right? And so like therefore they're probably not like noise. And so that's what ransack is. If we take 580, you guys like you'll implement this in class, I think. But yeah, this like important algorithm. And like by the way, for all the algorithms I mentioned before, they're all either in CV2 and ROS, so you don't have to ever worry about like doing these from scratch. But yeah. Okay, like this is our last like pure CV section. Like oh, I erased it. But like, what was like a main drawback of the pinhole camera model, right? Like go on.
You don't get that.
You don't get depth. Exactly. Oh, I guess I gave it away, depth estimation. But yes, you don't get depth, right? So like a person that's 5 foot tall could look the same as a person that's 10 feet tall or a building that's 10 feet tall. You just don't know the depth. And so like the reason, I mean, one way to combat that is having two cameras, right? That's what we do, right? We can approximate depth by looking, our brains do it for us automatically, but we look at the difference like that these two cameras see, like basically approximate depth, what like from like the difference, right? And that's called stereo vision. So like stereo vision is when you have two cameras, usually looking at the same thing, and then through that you can like estimate depth. So yeah, that's kind of what I talked about. And then and like for depth map computation, like this, you can derive all this from like what I just mentioned, but like I'm pretty sure these like the difference in like the two images that you got, and then B is like it's like some measure of baselines. Like you recognize, or as humans, we know that this much is about a feet. But you need some sort of mesh distance. So like this is like analogously, this is like the translation of rotation matrices. It's what we impose on a world. So we decide on. And then from that we can like get a depth in the units of whatever be your baseline distance is. And this equation you can derive straight from like the matrix that I mentioned before. And it makes sense, right? Like as your distance increases, your depth probably is like smaller, right? It's like the only way because like things farther away, like the farther away something is, like there's not that much difference like in my two images. But it was like really close, like this thing will see something really different from this thing, right? Any questions? Huh? Huh? The disparity is usually just like shift, like distance, like the literal like difference in images. Oh, now applying our concepts, how would we find the disparity? Okay, yeah, and how do you get optical flow? Using the what? Yeah. Oh yeah, we need core induction. Yeah, just like we would just essentially again apply our feature matching algorithm. We get the features, we map the features, and then we compute the differences between two images. Except now the interesting part, I guess, in this context is that we're not comparing images across time, but we're comparing images in the same time step for two different cameras. So like basically the same thing, but a little bit of nuance. Okay, so we're done with CV. At least for today. Next week we're gonna go and do SLAM with Alan, and other things. But on with some machine learning basics because I don't know the poll said so. So, what is ML, right? As I mentioned before, like with ML, like you're trying to approximate some model of something, right? And the most important part is that you recognize that the data that you might sample from the unit from like your world or whatever is finite. It's like an infinitely small subset of whatever you might experience. So you want to develop models that not only work well from the data you sample, but generalize well. Like on unseen data, it's still like it's a pretty good approximation, right? That's the key point. So again, going to some like types of machine learning, there's supervised learning where you give the model like a set of like XY pairs, and like so like given an input, like it has to predict the output. That's supervised learning. Unsupervised learning is where you give like a model only just the inputs and nothing else, and it has to learn like the labels on itself, or it has to assign labels by itself. So I guess a famous example is like clustering versus like KNN, where in clustering like you get a set of points, and you're just trying to like like group points together. You assign to each group like an arbitrary group. That's unsupervised learning. Vice versa. Okay. Does somebody want to take a gander as like what is more popular these days? Unsupervised learning or supervised learning, given the recent advancements in like compute power? Is unsupervised learning more hot or is supervised learning more hot? What is so in the past, right? With machine learning, the limiting factor was what? We don't have compute power. Like these models take too much to train. Like we just don't have enough compute power. But that's been solved. Not solved, right? But it's machine learning is like possible nowadays because of the GPUs and whatnot. So what is the main limiting factor in training models? Yeah, sorry. Okay, data, you're getting close. So what is expensive about data? What label data? Why is label data expensive? Yes, you need to pay people to label them, right? And that's expensive. A big example is like the internet, right? There's a lot of data on the internet, but the issue is that when you want to train for any task, you gotta hire a person to go through and like if it's for summarization, you gotta hire writers to summarize data, or like vice versa, right? It's really expensive. So what's been really popular these days is unsupervised learning, right? Because we already have a bunch of data out in the real world. It's not labeled, but we're fine with it, right? And like as you guys, and if you guys don't know this, but like in the machine learning world, like the more data, the better, right? So like, for reasons, unsupervised learning has been like really popular recently. And like a second reason it's popular is something called transfer learning. Does somebody want to guess why supervised learning is like restrictive in a sense? Like in the context of GPT, for example. Like why, like training a model to like summarize a given paragraph. Why is that restrictive? Who's next on the chopping? Why, why is supervised learning like restrictive in a sense? Like why is it constricting? Like why is it oh, I mean, he has an answer. Okay, yes, you have to have like that, like, but that's like a labeling issue, right? Well, I'll just answer it. It's restrictive because like if you think about like what it takes to like summarize something, you have to learn all of English, right? And once that happens, then you can summarize. It's like, and like for a different task, maybe for like text output like generation or sentiment classification, you still for every single one of these tasks, you have to learn all of English and then have this like final thing, right? So what's been popular these days is to like use unsupervised learning to like learn some broad thing about like the data, like understand English, for example, and then fine tune it on some supervised tasks at the end on like a much smaller subset of data, right? Um, and the reason it works is because you don't need to have labels to like learn English. And like a really popular technique is called masking, which is where like you give a model like a bunch of sentences and then you just mask a word, you like block it out and ask it to predict what's there. And the reason that works is because you don't need a labeler to like mask out like parts of text. Like you just mask it, right? There's no extra cross you need to like have that quasi label. So yeah, so what I just mentioned the transfer language which is like when you compute like a bunch of feature vectors for a given input, you basically like collapse the entire space of all sentences in the English language to like a bunch of vectors, right? Again, here's a concept of features and like decreasing dimensionality for better processing. And then you like, depending on whatever task you may have later, you additionally train on those input feature vectors on some downstream task. And I think in the context of computer vision, something that's been really popular recently is called Dino V2. Like Facebook released it like maybe like a year ago. But the reason it's so good is because like they're able to like make like really, really good like feature vectors for images and for videos. And it's like impressive because like they're like they're able to like basically again get feature vectors from input images, right? And like they're a way they show it's good. And by the way, this is like again an unsupervised model or self-supervised. They call it self-supervised, but it's the same thing, right? It's self-supervised model that like basically just outputs like embeddings for like a given input image. And like they prove it's good basically by showing we've like trained on a bunch of downstream task depth estimation, semantic segmentation. Like that's what is like estimating the depth, right? semantic segmentation, which is like drawing out like images of things in an image. Industry retrieval, right? Like comparing images across different sets. Dense matching, right? They're able to like, train it on all these downstream tasks. And like all of them work well, which must mean that like the embeddings that it comes up with must be like of some substance, which means that what? It was able to learn, understand the world part of like any like supervised learning task like really well, right? And like a lot of like the recent papers have been around like taking like the really nice embeddings that this gives you and like applying it in a smart way on some tasks. Like the reason that transfer learning and like this sort of thinking is like really huge is because like now people can design like ML algorithms in a different way. In the past, it was like end to end, right? Yeah, but you do everything from 0 to 1. But now you can say just take any like arbitrary like embedding model or whatever, and then do my stuff at the end of it. And the nice thing about that is that your algorithm is only going to get better like over time, right? As these embedding models get better and better, your algorithm will only get better as a result. Which is like a really powerful way like that people have like a way of thinking that people have been like sort of like using more and more. And yeah, and like I'm kind of like you can kind of tell from like all these problems, but like at some point, like whatever I just talked about is gonna be obsolete, right? Like already like some of the things I talked about is obsolete. Like I know for a fact that like I think death estimation has been like basically like stereo vision is not necessary anymore because you have ML algorithms that are able to like more efficiently like predict death based on an image. So like whether you should take 580 in the future, I don't know. I don't know if it's gonna be that useful, but like it's definitely nice to have like the basics. But like yeah, like machine learning like will like basically get you like 90% of the way there, which is like what you need for most tasks, right? Especially if it's like high frequency. Okay, anyway, we're just like we're talking about right now. And then lastly, reinforcement learning. This is probably like the most untapped part of learning so far. Like the first I've been like explored a lot. Reinforcement learning is still like relatively in its early stages, but I think it's most important because anything in your world that interacts with the world, it would just be reinforcement learning, right? The first are about like given an X, predict a Y, or given an X, learn something about it. Reinforcement learning is like you have an agent in a world, and then like it receives rewards in the environment, and like based on that, like predict like the best action to take. And it's like that's sort of a different paradigm that is important because you can frame supervised learning and unsupervised learning as a reinforcement learning problem, but you can't do it the other way around. But like reinforcement learning is like kind of a superset. But that's also like why it's like harder to like do because it's like a harder problem inherently. But yeah. Okay, so as I mentioned, right, you assume that you're trying to approximate some model of the world f of x plus epsilon, where epsilon is like the inherent like stochasticity, some randomness in the world, right? And your goal is to like train a model f hat of x from some data, from some data set D that approximates f of x. Okay, and usually this D, or always this D, is going to be a set of x and y pairs that you draw hopefully randomly from your distribution, your entire input distribution. Yeah. And then your goal, actually, like what this equation entails, like not only like in trying to approximate f of x, you want an f of hat that not only works well on D, but works well on other Ds that you might draw in the future. And that part is generalization, right? And as I said, or I haven't said this yet, but so D is usually called the training set, or rather from your data set, you just split them to like halves. You first train out some subset, and then to like kind of evaluate its generalization properties, you like kind of treat like the set that you held out on it as like a real world test. Like, oh, like let's see like how the model will do like on data it's never seen before. And that's like a way to like benchmark its performance. I say validation and testing, and that's because it turns out that, or maybe you guys noticed already, but these models that we have parameters to them. So like usually we want like a set to like train these like hyperparameters on. And then like a test set, which is like the actual test set. But yeah. And as I said, to get features and labels, if it's supervised learning and models, like you can be, linear regression, decision trees, blah, blah. If you're interested, take 520. Okay, cool. So as I said, like usually the model just starts with some parameters. It like tries to make some predictions, and then you most importantly have a loss function, where like you map each input x, each label y, and each prediction f hat of x to like some sort of loss. And the goal of the model is to drive down a loss. And some common loss functions are MSD and cross-entropy loss. You can switch to that if you're interested. And yeah, and so you can think of the model parameters and weights as knobs. Like what the learning algorithm is trying to do is just like tune these knobs such that the loss goes down, and hopefully reaches like a minimum. Okay. So now it's a gradient descent, right? So I think it's how many of you guys here have heard of gradient descent? Seriously? Nobody else has heard you? I feel like okay. Oh, okay, well. This is this is gradient descent, right? So like as I said, okay. So your x-axis, so like this is a graph of loss, right? So like y-axis is obviously gonna be loss. Does somebody want to guess what the x-axis is gonna be? Like what is the axis? What did I write here? Who is next? One. Okay, that's one of them. What else? What parameters are weights? I mean, I guess parameters are kind of all you need. I mean, I was also thinking about like your inputs. It's like because like with just parameters, you get a whole like world of losses depending on the input, right? But like with parameters and inputs, you get like a specific value. So like usually like the loss function looks like this, right? And your goal is to find the set of parameters essentially over like such that it minimizes the expected loss over your. So I guess the way I did this was like fat. Like I should do like give x, EF loss over like your distribution x, and then like as Juan said, this will be your parameter. So you're trying to find this point, basically. Who knows? Wait, somebody who knows gradient descent, like describe to me like how this works. Let's say so like initially I talked about like a model initialization step, right? So initially you start with some random, or it doesn't have to be random, but you start with some starting set of parameters data. That's what the model starts at. So you maybe start at this way, let's say. How do you figure out how to go here?
Find gradient, find the gradient of the current points and to modify your current points along the negative direction of the gradient.
Well, why is a gradient useful in this context?
Gradient is the direction.
Yes.
Describes the direction where the value or loss goes up first. So when we go the negative direction of it, we will go down. Those will decrease.
Yeah. So gradients are useful because they encode the direction that the curve is going in. So this is like a really like simple example because I made it one dimensional. Like in real life, like your theta is gonna be like many dimensional. So like it's like it's like an insane manifold of like a bunch of different curves and stuff like that. But the idea is that your gradient basically points in the direction of like where you need to go. And like just empirically speaking, let's say you're here, right? The slope is something negative, and it turns out that our loss is something negative. Or like yeah. And over here, the slope is positive, right? So you want to go backwards. So like turns out like the like slope or gradient is like in the opposite direction of where you want to go, which is why you make your new waves equal to the old ones plus the negative of your gradient plus some learning factor. And that's because like okay, actually, does someone tell me if alpha was 1, if there was no learning factor, what would happen if I started here? Yeah, so like if alpha was 1, you just jump directly down here, right? Oh, was that what you're saying? Well, that's what you want, right? You want to find a point where, yeah, exactly. So like the issue is that like if you're here and alpha is 1, it's just gonna jump straight down here, out of which it can't get out anymore, right? It's like there's 0 gradient, you're stuck. Okay, so you reach some minimum, yeah, but it might not be the best minimum. Like I could like pathological give you an example where like loss is always down here, or down all the way down here, in which case like your thing is like terrible, right? So you usually want some learning rate so you don't overshoot or undershoot rather. But that's just not it, right? You can always think of examples where like for any alpha I give you, you can like come up with some loss function where like you might get stuck in some place. And so like there are ways to combine like go around this, right? There's something called like a parameter with momentum where like you can imagine like this as a ball and like it rolls down with momentum. So like it won't get stuck into a gradient unless it's like a huge gradient, right? I think that's called Adam. Is that Adam? Yeah, I think that's called Adam. Adam learning, or not Adam, like Adam laws or Adam optimization. Something Adam. There's also SGD, which is this is mainly um in part because like usually your input data is like huge, so like you want to learn on batches. So SGD just basically takes the average, right? Because like recall that for my loss function only gives me a value for one x, right? So it could be the case that like for one input, you want the gradient to go in this direction, but for another input, the gradient wants to go in a different direction. It's like how do you decide, right? So SGD just basically says, all right, I'm just gonna take the average of like whatever the losses in my batch are and their associated gradients. Okay, and mini batch just like high level overview, you're just trying to like make you're trying to minimize the variance, or maybe you're trying to basically normalize like the updates to the weights you make in every like layer or something like that. But like all these are just to address like the speed and like the stability of your convergence of this gradient descent function. But yeah, all machine learning, I'd say, or like 99% of machine learning is just all using this algorithm basically. So it's like super important. Um, okay, and this is like I think the last slide for today before we go into our task. But how many people here have like heard about the concepts up here, overfitting, underfitting? Okay, most people. So who wants to explain overfitting?
Basically, if we have our test set and a model,
Or like not so like high level, like what does overfitting mean?
it means we can generalize to a larger
Yeah.
set of data.
So like overfitting is like when you've trained too well on the train set. Like, and like this kind of happens, like let's say that let's say like my train set, like let's say you're trying to approximate, I don't know, like a sine function, right? So let's say like, we know that the true like function is like this, right? Oh God. We know that the true function is this, right? And then when we sample a bunch of points D, we might get what? We might get like this point, this point, this point, this point, right? And then so overfitting is basically when your model like does too on the train set. So like an example could be like you go like this, right? This gets zero error on a train set. It's predicting every training set point correctly, but it doesn't generalize well, right? So this is called overfitting. Does somebody want to explain what underfitting is? Yeah. So yeah. So like underfitting would be like, I don't know, you like your approximation like this, right? It's just terrible all around. And like, does somebody notice a pattern between like this black curve that overfitted and then this black curve that underfitted? Like, what is the difference in these two? Like, what trait is different? Yeah.
The one that underfitted is like linear curve, the one that overfitted is like degree 4.
Okay. So like, so the overfitted one is more or less complex than the underfitting one. Okay, yeah. So like generally speaking, like if your model is too complex, it might learn it did a too well. Right. And remember our initial thing, right? We're trying to learn a function f hat that approximates our true function f of x. So if you choose like a class of functions that is too complex, like if you choose like an f, like all polynomials of like degree 6, for example, and the thing you're trying to fit is only like degree 2, like you've overfit already, right? Your model, or like it's possible to like train it, but like your model is probably just gonna like choose like a set of parameters that like fit the points well. Like it's not gonna generalize so probably. Um, and like the latter is like applies the same, right? If your model's too simple, like it's just not gonna work out well, even on both on training and on test. So there's like ties into the idea of like bias variance trade-off, which basically tells you that. Does someone want to explain to me like what this equation on the left hand side is? What does that mean? Who's taken 160 before? Or who's taking? I think all of you guys are taking 160 basically. So like what does like in like English, what does the left hand side mean? Yeah, so it's like like over, right? Over your entire distribution in the stochastic associated world, what is the expected difference between the true label, right? Y, and like your model, your approximation of that, right? So this is basically our loss, right? It could be MSC or whatever, right? This is our approximation of loss. And it turns out that this loss function can always be decomposed into like these three terms, right? A bias term, a variance term, and then this sigma squared, which turns out to be, I think turns out to be just like the variance of epsilon, like by definition. It's called like Bayes rule, or not Bayes rule, Bayes error term or whatever. It's just like this constant fact. It's like this is like error that can never go away. Like this could be due to like noise in a training set, or like your like labelers being bad and giving you wrong data. But this error can never go away with. It's always a constant. But these two things you can turn off, right? Because they contain f hat. And that's what we have control over. So like what are bias and variance, right? In this context. So there's some math here, like don't get like overwhelmed by it, but like the top term is what I said like above, right? That's just our expected error. And like bias is defined as, and it's like for those who haven't seen it before, like an equal sign with like a delta above it is like it's just like a definition. So like we're defining bias as the following, right? We're defining it as the expected difference over the distribution between your predicted model and a true model, right? So what does that mean here? Um, let's say let's say this is your true model, right? Actually, I don't want to do this. Let's say that your true model is like some polynomial that looks like this. Okay. Can somebody tell me what like a high bias looks like? What would give you a high expected difference of this over like the draw over data set? Do people even know what it means? Like, do you even know what EFD means? So this just basically means that I have like an entire input space, right? And I sample data from it, right? This just means that for like I sample data from it once, that's one instance. I sample a different set of data from it the second time, it's another instance. So like let's say like instance one, like you sample like these data points, right? Instance two, you sample like these data points, right? And then like instance three, maybe I don't have more already. Instance three, you sample like these data points, right? This just says that across all possible instances of your data draws, what is the difference between your model and like the true model, right? And so like a model that has high complexity as we defined would have high bias because wait, hold on. Yeah, it would have high bias because like let's say it's a degree of like a polynomial of degree 6, right? It might fit this model as like, oh sorry, wait, I'm mixing up definitions. Hold on. Okay, yeah. A polynomial, wait, so a polynomial of high complexity would have high bias or low bias? So let me answer. I'll draw a few pictures, like maybe a polynomial of degree 6 might fit this curve as this, right? And it might fit this one as this. Right, and then fit this curve as this. Right? There's a bunch of squiggles, right? For each of these instances, what is the difference between your true model and over your true model and like your model over like the given data set? What is the difference? For each of these instances. It's right there. Okay, let's say for instance one, right? This is the initial curve. Right? What is the difference between your true model and your predictions for only just this instance? It's 0, right? However, for the next instance, what is the difference? It's also 0, right? It's 0 for everything. It fit the training set, it fit D perfectly well, right? So in this case, our model has really low bias. In fact, we have 0 bias. It fit the training set perfectly, right? But let's look at variance now, right? Variance is what? Defined as the expected over the draws the data set of the expected difference between like between two like between like the average model and like the model that we got specifically. In other words, like ignoring like the equation on the right hand side, this is just like the definition of variance. Like the variance of D of a model F is just like across draws, like how much does our thing differ, right? It's like just looking at this, like just visually, the same model like looks really different across different instances of your data set, right? Which means that your model has high variance, right? A model with low variance would be something that has like that's like usually not as complex, right? Like maybe a straight line, right? A straight line would have um like a data like a line would approximate each of these instances like pretty similar, right? Right. So, like for the first data set, it would have like drawn this line. For the next data set, we're drawn this line. For the next one, we're drawn this line, and then like this line, right? Like the variance across these instances are it's like low, right? So simple models have low variance, right? But as a result, they suffer from high bias, right? For each of these models, it has terrible loss in every instance, but there's not that much variance in between like individual models, right? Across different draws of data. On the other hand, our like really complex model has really good training loss, right? Has really low bias, but there's a lot of variance between like different draws of the data, right? And so like we kind of see this variance, like bias variance trade-off happening where like for any given model class, like there's a trade-off and we're just basically trying to find a model class that minimizes these two values in a sense. Um so so yeah, like can somebody explain to me like why you would want your model to have like it's obviously clear why you want your model to have low bias, right? You'd want your model to do well in the training set. But why do you want your model to have low variance across the draw of the distribution? What is variance like a metric for? Like almost. What's it mean? Or kind of like, okay, how about this? Let's think about it this way. Let's say that we had a true model F, right? Like, let's say F of hat was like, we had a perfect F of hat. What would the variance, what would like var D of F of hat X comma D be equal to? It would be equal to 0, right? You guys see this? The true model for this initial data set would be still the black line, right? The true model for like these set of other points will still be the black line. The true model is always going to be true model. Like no matter what data set you give it, the way we learn it is going to be true model. So like, let me phrase it a different way, right? If we're really so confident about what about the quality of our F of hat, it shouldn't really change much, like depending on like whatever inputs that we give it. Like, um, does that make sense? Like, it shouldn't. If it's really the true model, like what it looks like shouldn't change drastically depending on what we train it on. It should all look kind of the same, right? Because it's a true model, it shouldn't change at all. It's only one model, right? So we want our models to have low variance. Like that does that make sense? It's fine if it doesn't make sense. Like, but I can like re-explain it. But like you want low variance because you don't want your model, like the true model wouldn't change much across like different training sets it trains on, right? If your model change a lot, depending on whatever you feed it in, that means your model is not correct. Because remember, your model is all like your f of hat is trying to approximate this constant model f of x, right? So it shouldn't change at all. Like f of x is constant. So like so if you're training a model and like you realize that the outputs of your model, like the curve of your model looks really different depending on what you give it, that definitely means that you like have the wrong model because it shouldn't change at all, right? High variance is bad. And that usually means that you're overfitting, right? Your model is too complex. And so going back to this graph, right? This is in part like when you're training a model, why you keep track of like testing losses and training losses, right? It's like, all right, I guess to hide this away, like as you train a model for more and more epochs, as you apply gradient descent for more and more like iterations, would you expect your training error to go down or to go up? Your training error, your error on your train set. It would go down, right? Because that's what gradient descent is about. Gradient descent is about like giving a loss function over your trained data, tweak the parameters in ways such that your loss goes down. So your training loss is always going to go down, right? Unless your model is like not complex enough. It's like, let's say you're training like a line on this data. A quick way to see that your stuff isn't working is if your train error is just it goes down for a bit and it kind of stays constant and doesn't go down to 0. That means your model is probably not complex enough, right? It's just not, it's impossible. It has high bias, right? No matter what you do, it's never going to capture the data well, right? So if your loss is constant, it doesn't go down. Your training loss, if like even the training loss isn't going well, you got to revisit what model you're choosing, right? Okay, so training loss in theory should always go down if your model is complex enough. How about the testing loss? Over the course of time, does it go down or does it go up? And like, remember, what is testing loss a proxy for again? Yes, of the real world, right? The testing loss is like we're basically testing the model in real life to see how well it actually do and how well it generalizes, right? Like what do we expect testing loss to like behave as we continue training?
Let's go down, but as the training goes, will go up.
Yeah. So initially, right, as the model is still learning like the basic things, the testing loss is obviously going to go down because initially it's just like random stuff. It's like predicting random stuff. It hasn't learned anything yet. So initially both training and testing loss are really high, and they're both going to go down, right? But at some point, your testing loss is going to go high, right? Why is it going to go high after some point?
Starts overfitting.
It starts overfitting, right? Your model has learned to train it too well, right? It's overfitted, right? Like if you imagine like, I'm gonna erase the lines because it's making it too messy. But like, again, our tree data distribution is this, right? Let's say, right? Initially, your model looks like this. Your model is like really random. It's like completely bad. But as you train, it like slowly starts. And sorry, and let me also draw like the points that are in your data set. Right. Initially, it's like really bad, but as you train towards these data set points, like it kind of like gets closer and closer. Right. So training loss is definitely lower than before. Validation loss is also lower than before, right? Because it's still somewhat closer. But eventually, as you keep on training, you start overfitting, right? Like at some point, you like you fit the points too well. Right. Your training loss is going down, but your validation loss has increased, right? Because like in pursuit of excellence on your training set, you've like, I mean, you like basically, I mean, you are ignoring the test set, right? Because you don't get access to it. But like in pursuit of making the train loss like exactly zero, like the rest is shit, basically. And it's like that's why like variance is almost a proxy for generalization, right? Because if your model like does well, even on unseen data, if it generalizes well, that means it has low variance. Because that means across different draws of the data set, your model stays the same. Right? Okay. Any questions? Oh, sorry. For that. Like, so like just a recap, right? You're underfitting here. This is like pretty good. Right. This is a case where the data is noisy, if you guys can tell. Right. You're overfitting if you're trying to like fit into every nook and cranny, like what it looks like. Right. And like the middle is kind of the happy ground. So like as I said before, your training loss or your bias is always going to go down because bias is a measure of what? How well your model fits to the data. So it's training loss. Right. Well, right. Your validation loss or your variance is going to go down initially and then up because it's gonna learn and it's gonna overfit. Right. And what is loss? Like your general loss, right? It's a sum of bias and variance, right? So that's why general error goes down and it goes up again. So like we want the model that has the lowest general error, right? Because the lowest general error is like the lowest loss over the entire distribution and over the entire like stochastic network. So you want to find this point. So what people sometimes do is called early stopping, where it's like you train a model, train a model, and you stop the moment the validation loss starts going up. So that means you hit your sweet point, right? Okay. That's it for teaching for today. Any questions? Okay, cool. On to the first task, like get your computers out. We have an hour to do this. I don't know if we have enough time to be honest, but that's our first project or not project, first task. Like I talked about all these concepts. But like this we have like two kind of tasks that like nicely tied together. So like first one is like deploying like an image recognition model to your phones. So that will be in digit classification.py in the mono repo. But what's gonna happen is that I've already trained like a digit classification model for you guys for this week at least. Next week we're gonna talk about PyTorch and all that stuff. And next week you guys are gonna train it yourself. But like for this week I trained it for you. I'm gonna give you the weights, the parameters I've trained that I think are good. And then you guys are gonna deploy onto your phone, right? Like what would that involve, right? You need to have a CV2 pipeline that takes an image, right? Applies some sort of transformation for it to match whatever I trained the model on. It's like, how do you get from here to here? Right? You want maybe some thresholding, maybe some blurring, maybe some, I don't know, like rotations to make sure it's the right orientation, stuff like that, right? So that's first step, what we just learned. And then, I mean, the rest is just inference. I set that out for you. So like all you have to worry about is this step. Okay, cool. And yeah, that's it. I think it's just digit recognition.py. Yeah, and you guys will just finish the process function. Everything else has been done for you. Get started. Yeah.
Two general question, why we call this course, crash course? The name,
It's like introduction.
okay, and, how can we can,
Like Ross, we just finished. We're gonna go research. Basically, like.
yeah,
Like, you guys said like, publishing a receiver, so like, the tools and then we got like a script that we receive. We extend like. The placeholder, we'll set images and like, which was money. Set up instruction. I remember all this. And know about it, like, we're trying to like, do integration with this, like, I guess, like. The capital, something I did have done, or totally weird.
Are we doing this?
Huh? We'll see.